A double integral finds the volume trapped between a curved surface sitting above a flat region and that flat region itself. Let's begin with a worked example over a rectangular region. Here the surface is f of xy equals x times y, and the flat region below it is the rectangle where x runs from 0 to 2 and y runs from 0 to 3. On screen, imagine a flat rectangle sitting in the xy plane, and above it, a curved sheet rising up wherever x times y grows larger. We will show this rectangle first as a flat two-dimensional view, then lift it into a three-dimensional picture with the surface floating above it. In words, the double integral over the rectangle equals the integral over x from 0 to 2, of the integral over y from 0 to 3, of x times y dy dx. In symbols, that is integral from 0 to 2, of integral from 0 to 3, of x times y dy dx. We integrate with respect to y first, treating x as if it were a fixed constant number. The integral of x times y with respect to y is x times y squared divided by 2. Now we plug in the boundary values for y, which are 3 and 0. At y equals 3, we get x times 9 divided by 2, and at y equals 0, we get 0, so the inner result is 9 over 2 times x. Next, we integrate this result, 9 over 2 times x, with respect to x from 0 to 2. The integral of 9 over 2 times x with respect to x is 9 over 2 times x squared divided by 2, which simplifies to 9 over 4 times x squared. Plugging in the boundary values for x, at x equals 2 we get 9 over 4 times 4, which is 9, and at x equals 0 we get 0, so the double integral over the rectangle equals 9. Check step. The function x times y stays positive everywhere on this rectangle, since both x and y are positive there, so a positive volume of 9 makes sense. Now let's set up a double integral over a general region, one that is bounded by curves instead of straight edges. On screen, picture a flat two-dimensional region squeezed between the curve y equals x squared below and the straight line y equals x above for x between 0 and 1. We then lift this same region into 3 dimensions, showing a curved surface f of xy equals x plus y rising above that curved sliver of a base. In words, for each fixed x between 0 and 1, y ranges from the lower curve, x squared, up to the upper curve, x, so the double integral equals the integral over x from 0 to 1 of the integral over y from x squared to x of the quantity x plus y dy dx. We integrate the inner part with respect to y first, treating x as constant. The integral of x plus y with respect to y is x times y plus y squared divided by 2. Now we plug in the upper limit, y equals x, which gives x squared plus x squared divided by 2, and that combines to 3 over 2 times x squared. Then we plug in the lower limit, y equals x squared, which gives x cubed plus x to the 4th divided by 2. Subtracting these, the inner result is 3 over 2 times x squared minus x cubed minus 1/2 times x to the 4th. Now we integrate this expression with respect to x from 0 to 1 term by term. The integral of 3 over 2 times x squared is 1/2 times x cubed. The integral of minus x cubed is minus 1/4 times x to the 4th, and the integral of minus 1/2 times x to the 4th is minus 1/10 times x to the 5th. Plugging in x equals 1 and subtracting the value at x equals 0, which is 0, we get 1/2 minus 1/4 minus 1/10. Using a common denominator of 20, that is 10/20 minus 5/20 minus 2/20, which leaves 3/20. So the double integral over this general region equals 3 over 20. Check step. Since x and y are both positive across this whole region, the quantity x plus y stays positive, so a positive final answer of 3 over 20 confirms the volume sits correctly above the region.